Hi everyone. In this final M4 hackathon, my objective was to build a reliable and high-performing classifier for the UCI bank marketing dataset and maximize the ROC/AUC on the Kaggle test set. I focus on ROC/AUC because it evaluates how well the model ranks positives above negative across all thresholds, which is especially useful when the classes are imbalanced. In this video, I will answer the two required prompts: what I did to improve performance and what I did to access and improve model fit. To improve performance, I started with a clean package safe pre-processing and modeling pipeline. I separated features into numerical and categorical columns automatically. For numerical features, I used median imputation to handle missing values, and then applied standard scaling so that models like logistic regression are not dominated by feature magnitude. For categorical features, I use the most frequent imputation and one-hot encoding with ignore unknown categories. So the model can still score test examples that contain categories not seen during training. I put these steps inside a single column transformer pipeline so the exact same preprocessing is applied consistently during cross-validation, turning, and final training. Next, I compared multiple candidates models using a stratified five-fold cross-validation with ROC/AUC. As, uh, as the Socrates metric, I evaluate four model families: logistic regression, random forest, extra cheese, and histogradient boosting. The goal ha the goal here was not only to meet evaluation requirements, but also to quickly identify which model classes best matches the structure of the data. In my results, the G-based models performed better than the linear baseline, which suggests the problem benefits from nonlinear interactions and con- con- condi- conditional splits. Based on the baseline ROC/AUC ranking, I selected the best performing model family for deeper turning. After choosing the best model family, I applied a hyperparameter turning using random size search CV to improve performance beyond the baseline. I turned the model's specific parameters. For example, for histogradient boosting, I searched learning rate, max dips, number of boosting iterations, minimal leaf size, and L2 regulation. Random size search is a practical choice here because it explores a wide space more efficiently than exhaustive grid search. Importantly, I run turning with stratified cross-validation and evaluate using ROC/AUC. So the turning objective matched the Kaggle leaderboard magic. After the search, I selected the best estimator from the turning results and then refit that best pipeline to the full training set to produce my final model. For the second prompt, assessing and improving model fit, I used a combination of a holdout validation check, cross-validation results, and a learning curve. First, I split the training data into a training and a validation set using a stratified split. The purpose of this holdout set was to do a sanity check that turned the model generalized beyond the specific folds using inside cross-validation. After turning, I evaluate the best model on the holdout set by computing ROC/AUC using predicted probabilities. This let me confirm that the model's performance is not just a cross-validation artifact, and that it generalized responsibly well to unseen data. Second, I generate a learning curve using RCUC to assess whether the model is underfitting or overfitting. The learning curve plots training performance and cross-validated performance as the number of training examples increases. If the training curve is high but the cross-validation curve is much lower with a persistent gap, that indicates overfitting, meaning the model fits the training data too closely and does not generalize as well. If both curves are low and close together, that suggests underfitting, meaning the model is too simple or not trained effectively enough. In my learning curve, I use the trend and the gap between the curves to judge fit. If I saw overfitting, I would rely on stronger regulation or constraints such as increasing minimal leaf size or limiting dips. If I saw underfitting, I would consider allowing more iterations or a slightly more complex model. This learning curve step is important because it connects performance to model capacity and data quality, rather than just trying changes blindly. Finally, to ensure my Kaggle submission aligns with ROCUC, I submitted predicted probabilities rather than hard class label. ROCUC depends on ranking, so submitting probabilities persuades more information and typically improves the score compared to submitting 0 or 1 predictions. I also ensured that the submission file matched the requirement format exactly. Two-column named ID and target, where ID matches the test set ID column exactly and target contains the model's predicted probability for the positive class. To summarize, I improved performance by building a consistent preprocessing pipeline, comparing multiple model families using stratified cross-validation with ROC and then applying random size search CV to term the best model family. I assessed and improved fit by using a stratified holdout validation check and deploying a LC learning curve to diagnose underfitting versus overfitting and guide how I would adjust the complexity and regulation. This workflow helped me align the entire modeling process, pre-processing, turning evaluation, and submission with the ROC objective used by the Kaggle leaderboard.